Having looked at all the algebraic properties of determinants and how those play out, let's see how geometry is affected when we look at the determinants. So here's a linear transformation, and we have A specified, so we can find the determinant easy enough. We know determinant of A is just 5. Okay, so then we want to know what the effect of t is, and then how do we change the, or how do we see the determinant? Well, if we look at the unit square in R2, okay, because this is a 2 by 2 matrix, we can see that 0, 1, that as a vector is translated to the vector 2, 1, and similarly, the vector 0, 1 is translated to the vector 1, 3 by the matrix. Okay, so then we can say, okay, here is our post image of that same unit square after the transformation. Okay, and if we look at this, we can say, okay, the area is 1, and if we, before and then after, if we look at this, we could, find the area of the parallelogram, but the area is going to be 5. Happens to be the same thing as the determinant, right? That's curious. Okay, but and we could find the area using different formulas, but the big takeaway here is that the area of the parallelogram defined by V1, V2 is the determinant of V1, V2. Okay. So again, we could find the area just by the determinant. We've seen this before. Okay. So the expansion of the area, well, okay, I'm going to leave it there. Okay. Now let's suppose in general we have a 2 by 2 or a linear transformation from R2 to R2, and we have A as representing the transformation. If the determinant of t, or the determinant of A is non-zero, then t is invertible, right? That was one of our conditions. If the determinant is zero, then it's not invertible. Okay, and then consequently, if we're in R2, we could say it takes parallelograms to parallelograms. Okay, so if we were to draw a little image, okay, so imagine we have transformation t occurring, and we have, vectors, something like this. So we would have, over here is V2, and down here on the bottom would be V1 that spans this parallelogram. Okay, and we're going to call this general space omega. This is consistent notation with the textbook. So then if we apply the linear transformation, we're going to get the transformation of space omega, which is going to be our parallelogram. Could look slightly different. Okay, and so we have something like this, and here on one side we would have the image of V2, and on the other side we would have the image of V1. Okay, so nothing really new there, but if we look at the area, okay, if we look at the area of t omega, okay, according to what we saw above, this should be the determinant of t of V1 and determinant of t of V2, right? Okay, but then if we look at this more carefully, this is going to be the determinant of AV1 and AV2, because that is what t is by definition. Okay, and separating this out, this is going to be determinant of A, and then times the vector V1, V2. Okay, and then we can separate this out by the algebraic properties of a determinant and say this is determinant of A times the determinant of V1, V2, but, okay, this whole thing, determinant of A times, let's see, this whole thing here, that is just the area of omega, right? We started this whole thing by saying the area of this parallelogram is just T of omega, which we can define as a determinant, and so we end up with this result. So now what we can say is that given this relationship between area of T omega and area of omega, that the area expansion factor for this transformation is the absolute value of the determinant of A. And so we would get this by doing the area of T omega over the area of omega. So the determinant is telling us how much our area is scaled by after we transform. That's really all it is saying. And this idea, so we did this for parallelograms in R2, it actually ends up working for any region. And all we have to do is by limits. So we just have to, break each region down into a 2x2, and then remember that the transformation takes parallelograms to parallelograms, so we just have to do this a few thousand times if need be. But it ends up working for any region and in any dimension. Okay, so we will expand upon this in the next videos.